Hey, my name's Scott Jean, and I'm a PhD student at the University of Cambridge, and I'll be presenting our paper Low Emission Building Control with Zero-Shot Reinforcement Learning. This is joint work with Alessandro-Abating at the University of Oxford and Jonathan Cullen, also at Cambridge. The TLDR of this work is as follows. We introduced PEARL, Probabilistic Emission-Abating Reinforcement Learning, an algorithm which safely reduces emissions from energy-intensive equipment in buildings by up to 31% with zero prior knowledge. Because we can bypass the previously held requirement of historical data or access to a simulator for each building we'd like to control, we contend that this method could scale to every building in the world, unlike prior works. If this is interesting to you, please listen on. I'll begin by motivating the problem, with the first motivation being climate change mitigation. Here's a map tracing the global flow of energy from primary source on the left-hand side of the screen to final service on the right-hand side of the screen. If we focus on the middle slice of the diagram, we see that global energy use can be stratified into one of three categories. Energy used to create motion in cyan, energy used to regulate temperature in red, and energy used for everything else in black. We can observe that the primary source of energy consumption globally is in regulating temperature, approximately 50% of total energy demand. Finding ways of regulating temperature in society more efficiently could prove a useful way of reducing energy and thus carbon emissions. Another part of the diagram I'd like to draw your attention to is the blue section labelled renewables in the bottom left. Though renewables contributed to a small percentage of global energy supply when this diagram was produced, using data in 2005, the IEA expect renewables to contribute to 75% of global energy supply by 2050. Such a high penetration of renewables on the grid will cause problems related primarily to the stochastic nature of renewable energy generation, often a problem called intermittency. To explain intermittency, consider the hypothetical scenario of powering a home using only a solar array located on its roof. Here we plot demand for energy in blue and the supply of energy from the solar array in orange for 24 hours. On a perfectly clear summer's day, the energy supplied by our array will increase in the morning as the sun rises, peak around midday when irradiance is highest, and fall in the evening as the sun sets. In contrast, the occupants' demand for energy won't be so symmetric. They'll likely produce a peak in energy demand in the morning when they wake up, a plateau in the middle when they go to work or school, and a second peak in the evening when they return. These mismatched curves create periods where demand exceeds supply, and the national grid will need to cover the deficit by spinning up fossil fuel-powered reserves, creating unnecessary emissions that could have been avoided. Here's an illustration of an idealized scenario. Now we've added a storage medium, either electrical or thermal, and we flattened the blue demand curve, spreading it throughout the day rather than allowing the peaks in the morning and evenings. Clearly, traditional controllers cannot perform this optimization, so we need new techniques. A well-studied solution is reinforcement learning, which can solve this problem given arbitrary compute or data. Here I detail three of the seminal works in the RL for smart building control literature. Some authors report RL can improve energy efficiency by up to 35%, but all past works require pre-training of their agent in simulation prior to deployment. Such simulators can be difficult to construct, requiring lots of prior knowledge about the building, which can take an expert months to obtain and distill into a model using the favoured software, Energy Plus. To get around this bottleneck, some authors have reported results where the agent is deployed in the building without pre-training. In our paper, we call this zero-shot building control. LASIK and authors grant their agent a short commissioning period of 3 to 12 hours in the real environment to collect data and build a model. Their approach is suitably general for scale deployment, but only improved cooling costs by 9%, likely because they use a linear model that erroneously linearized the nonlinear thermodynamics of the data center. So this provides the context for our work. Here we make one guiding assumption. To scale to every building in the world, we must bypass the expensive to obtain simulators and perform zero-shot control. This begs the question, can we find methods that are as data efficient as LASIK, i.e. that use 3 hours of live data to build a model, yet perform as well as the agents trained in simulation, i.e. showing a 35% energy reduction? In this work, we answer our question with a new approach called PEARL. PEARL performs system identification during a 3-hour commissioning period, maximizing information gained by exploring parts of the state action space where the model is least certain about the one-step dynamics. Its model is an ensemble of probabilistic networks which it uses to plan via model predictive path integral and trajectory sampling. PEARL learns the system dynamics online with no prior training. We seek to learn a mapping F from current state in action to next state. Our model is an ensemble of probabilistic networks outputting a multivariate Gaussian over the state space. The Gaussian allows us to quantify aleatoric uncertainty in the predictions, and the ensemble allows us to quantify epistemic uncertainty, with the idea being that this improves data efficiency when operating in the online regime. We train the networks with the standard MLE loss. We plan by combining model predictive path integral, a form of model predictive control, and trajectory sampling. At each time step, we sample action sequences from an initially arbitrary Gaussian with mean mu and scales sigma. We pass these action sequences through our models p many times to get a distribution over the state action space at horizon h. This distribution gives us an expected reward for an action sequence, which we can compare with many other sampled action sequences to find our expected optimal sequence. During system identification, i.e. our 3-hour commissioning period, Instead of optimizing for expected reward, we optimize for predicted variance across particles. The intuition here is that higher variance in our predictions means higher model uncertainty, so collecting data in this region of the state space maximizes information gain. We formulate the problem of building control as a standard MDP with the usual state space, action space, reward function, and transition dynamics. Our reward is a linear combination of an emissions term and a temperature term. The emissions term is the grid price times our energy consumption at time t, and our goal is to minimize it. The temperature term is 0 if the temperature in the building falls between the safe bound defined between T low and T high, which are in practice set to 19 and 24 degrees centigrade. If the temperature falls outside these zones, the agent receives a large negative penalty in proportion to said deviation. In short, the task is to minimize emissions from the building whilst ensuring thermal comfort for 1 year without prior knowledge, historical data, or access to a simulator a priori. We perform experiments in Energym, an open source framework for testing RL algorithms and simulation. We use their mixed-use office and seminar center environments, which have varying sizes, equipment, and thermodynamics. Our baselines are 2 model-free algorithms, SEC and PPO, 1 model-based algorithm, MPC DNN, and the existing rule-based controller. We also baseline against an oracle, which in this case is a pre-trained SEC agent with hyperparameters optimized for each environment and trained for 10 years prior to test time. Our oracle represents performance in each environment with the constraint of no knowledge a priori relaxed. We find Perl minimizes emissions in the mixed-use facility, reducing emissions by 31% compared to the RBC. In the office environment, Perl outperforms each of the RL agents but is beaten by the RBC, and in the seminar center, all controllers perform almost identically. From a temperature perspective, Perl outperforms all of the other RL agents, controlling the building safely throughout the year. The green band is thermal comfort constraints, and Perl is only outside of it for 0.5% of the year in the mixed-use facility, 1.5% of the year in the office, and never in the seminar center. In contrast, the other RL algorithms miss it quite regularly, in most cases far too regularly for them to be considered safely deployable. We perform an ablation study to assess the effectiveness of our system ID policy with respect to the random walk policy used in LASIK's work, and a baseline of no system ID at all, each across different durations of commissioning period. After each commissioning period, we take the trained model and predict the state transitions of 100 held-out state action trajectories, finding that the predicted performance of our model, here denoted as MV for maximum variance, outperforms in expectation the random walk and baseline for all commissioning periods greater than or equal to 3 hours. We decompose Perl to identify which parts of the agent are linked with its performance, finding that, to our surprise, the use of probabilistic networks as opposed to deterministic networks has little effect on performance, and the use of MPPI as the planning algorithm was far more important. We observe empirically that Perl learns the load shifting behavior we would like to exhibit automatically, here shifting the load to times of day when grid carbon intensity is lowest, namely the mornings and evenings. As one would expect, the existing rule-based controller does not show similar capability. We conclude with 3 key takeaways. To scale RL control to every building in the world, we must bypass expensive to obtain simulators. Perl bypasses such simulators by operating solely in the online regime and safely reduces emissions by up to 31%. And performance correlates more with the planning algorithm than choice of model. Here are the details for getting in touch to contact us to discuss this work or future work, and please scan the QR code to read the paper and see the code in our repo on GitHub. Thank you very much for listening.